My name is Joseph Wunderlich. I'm a professor of engineering, architecture, and computer science. I'm recording this in spring of 2022. I was born in 1961. This lecture is on parallel processing interconnect architectures in an advanced course in computer engineering. It's for processors and cores as well as computer networks. This lecture is right now being recorded as a PowerPoint with embedded audio. It'll be saved as an MP4 and uploaded to YouTube, as well as a PDF. The PDF will be in the comments. In lecture class for students, it's ideal to run the PPTX with audio and then click on the links and spend extra time where the links take you. In YouTube, you will need to go into the PDF to get to the links. We're going to discuss both static and dynamic architectures, as well as the network characteristics for the static and the scalability of both. Static interconnect architectures have a number of different topologies. You can see the linear array, ring, cordial ring, and barrel, and then exhaustively connected. Also binary tree and star and binary fat tree. Here's an example of a neural network chip that I designed and built in 1992. It was my second processor design. The first one's recorded in the patent office. It's more of a paper design. This one I actually fabricated and tested. And this is a binary tree that is type architecture for the artificial dendritic tree of feeding into neurons. There's 64 neurons here. This is analog as capacitors as well as digital on here, and a big decoder down the middle, and then memory elements, registers. We click in 4-bit values for the duration of the impulse into each of the 64 neurons. This is a star topology. This is our campus network at Elizabethtown College several years ago. We also have mesh, iliac mesh, torus, systolic array. 3 cube, 4 cubed, formed by interconnecting 2 3 cubes, 3 cube connected cycles. K-ary n cube, and then folded connections, torus, folded or not. Now we want to be able to assess each of these architectures for scalability, for feasibility to implement. So n is the number of nodes, where nodes would be your core or your processor or your computers in a network. We want to optimize that for the given applications and typical problem grain size. We've talked about in other lectures with grain packing and scheduling, and how you can parse a problem into a grain. Coarse grain would be where you can have a core or a node or a core or a processor or a computer work on a given problem without having to interface with the other nodes that often. Fine grain would be the opposite of that. Wire length is, or channel length, we call it inside of IBM, or the graph edge. You want to try to minimize. That's the wire length is directly proportional to the rate of degradation of signals over the length of the wire, and consequential loss in speed and performance. Capital D is your network diameter, and that's the shortest distance. That's the shortest distance to the furthest node. So here is D equals 4 in this architecture, D equals 3 in this architecture, and capital D equals 4 in this architecture. And we want to minimize the capital D to reduce communication delays. The small d is your degree, is your average number of connection channels into a given node, the average number. So here there's a different amount in each of these, whether you're on the corner or somewhere in the middle. You have 2 in the connections in the corners, 3 in the middle, so averaging 2.5 in this case. Here we have d equals 3 for all cases, or d equals 2 in this case here. And we want a constant d. If possible, it's better for scalability and modularity, having each node have the same hardware and software issues to work out. Capital B is bisection width. Is the number of links through the smallest cross section. So you lay out your architecture, and here's a plane going through this cube. Just draw a line through this one, line through that one. So we have B equals 2 here. B equals 4 through the cross-section of the plane. B equals 2 crossing this line. We want to minimize B to minimize required wiring. We also want to maximize B sometimes for network communication bandwidth, given connection. So there's trade-offs there, and so you have to balance and optimize this. And in general, as the capital B goes up, a small d goes down, and the little d goes up. Then we also want to discuss in coming slides the number of wires through a given connection, whether it's parallel or serial connections, and also whether you're packetizing or not on the serial line. Now, continuing on looking at these metrics, these characteristics of static interconnect architectures, and speaking more about the number of wires in one channel link or edge, one of the links. We want to recall, students in my courses recall parallel and combination, parallel, which is combinational digital design, and serial sequential digital design, and how that applies to these links here. So take a minute and just click my students in the class, click on these links, go into these courses, and just recall how this works. In general, a parallel combinational circuit, you just have stimulus and then response flowing right through. In serial, which is more applicable to what we're going to talk about here for these interconnect architectures, you have memory, and that feeds back, memory and feedback. This green line is a little hard to see here, but and then we have all this combinational digital logic, and the whole thing here is sequential. Synchronous is what we typically do in class here. There's also asynchronous and pulse. And then there's a finite state machine that drives that. And then an example here, which is not necessarily applicable to the interprocessor communication we're talking about with these architectures, but it is nonetheless communication where we have devices, we have peripheral devices, and via interrupts talking to a given processor, and you need some kind of priority encoder to make sure to decide who gets service first. And there's a whole lectures or 2 that we do on just these kind of things, including traps versus interrupts and how those work. So maybe pause here in lecture time and go through all of these things here with the students. Otherwise, it's more of a footnote here in the context of this overall static interconnect architecture. And look at the courses too. Now, this is what's more applicable to this static interconnect architectures here, where we have communication, serial communication between processors or cores. And so this is a serial line coming in, and a problem on how to solve that and design that using digital design methods, and characteristic and excitation tables, and the whole design steps of the process. You can see I've developed in my courses step-by-step processes for the students over the past 25 years for both combinational and sequential circuit design. Also need to consider whether or not these serial links are packetized, which is a whole other level of overhead. The data is just one part here, and then you have all the other overhead. In class, we can maybe go look at that. Although it's presumed students will look at this kind of thing in lower level courses that I teach and others teach. This is somewhat of a footnote or a tangent to talk about here, but we do and we have done packetized serial communication between systems in our robotics, and actually won an award, only one of 4 out of 50 schools at one of the international ground vehicle competitions, autonomous vehicles at a military base in Michigan. DARPA funded, mostly graduate schools, only a couple undergrad. Japan had 3 schools compete to see who actually got to compete at this event. And so it was a pretty intense kind of competition with several $100,000 worth of donations and several years of development. This was our 3rd entry into this competition over the first decade of the 2000s. And it's similar to TCP/IP, but is different. It's a military protocol, JAWS, used for actually communicating networks of military tanks on the battlefield. And in class, maybe go off and just click on some of these links here. I'm not going to do it now. We can't inside of an embedded PowerPoint, but this is the JAWS subsystem. There's other subsystems here, and I asked the students to leave good documentation for future students. And then publications that came out of it and what students ended up doing. This James Painter, we presented this paper down at NASA, or at a conference next to NASA in Florida, where there were all NASA people in there. And then James Painter went on to Stanford after working at Google and Intel. Now works at a company that travels back and forth to Japan and Korea every month when COVID's not on. David Coleman went and got his master's and PhD and now leads a research group at Johns Hopkins University. And then the developer of the JAWS wireless communication protocol, along with David Coleman here, Jeremy Krause. Don't list them here because this was not a publication. This was just an internal. What did I just say? Oh, it says here Jeremy Krause. And he went on to an automation company. And then this is really getting off topic here in this course, but this is a whole course I teach in robotics and machine intelligence. It could take a second to look at that during the lecture for this given course, although several of the students in this iteration of the course I'm teaching this lecture in have had this course too, so I don't want to be redundant. We have a whole evolution of robots here. We actually founded the robotics or the scholarship day at Elizabethtown College before anybody else did it. We had for 23 years symposiums. Now, scalability. So, in class we can take time and look at each of these more, but each of these architectures have a different scalability based on the metrics. Now I'm going to switch to dynamic interconnect architecture. So dynamic is the bus architecture that's common in PCs. It was common for most machines up until recently, still is most common, where you have a bus. And the bus is where you can have lots of things communicating with lots of other things with some kind of isolation, so that you can't physically hardwire everything to the bus all at once. You need tri-state buffers or some kind of isolation to electrically not have everything connected all at once. But the beauty of it is everything can connect to anything else. It's not quite as scalable as some other architectures, dynamic architectures, but it works pretty good in most cases until you get too many things trying to talk to each other. And then we want to talk about bus, start off with just a basic concept. This is from an intro course that I teach. I assume students get this kind of knowledge in other courses if they don't take the intro course. This was a requirement for all computer engineers, and well, there's a whole history for computer science and information systems students I won't go into here. But if the students are in this advanced class and have not had this, this is going to be a little bit new, but only because they haven't seen it from me. They should have seen it somewhere else. So the basic idea of the buses, both the data and address bus, is two different kind of things to think about there, especially when we switched from 32 to 64-bit addressing, as we did in IBM, and we need virtual address translations to only have so much physical memory, but all the software, operating systems, and programs thinks it has 64 bits, and so there's a translation. So that it gets more complicated, and take a look at that in other courses. Just in general, the data bus is as wide as possible. And you get on graphics cards, it's even wider than this because you want multimedia giant chunks of data. The bigger, the better. Address bus, there's only so much that makes sense because 2 to the 64 is a ridiculous number. It's just not a feasible amount of address space that would ever exist. So typically in processors would have 40 pins on the back, so you could have 2 to the 40 addresses for your memory. This is from a publication that I did in 1999. So I wrote this while I was a professor at Purdue University before coming to Elizabethtown College in 1999. And this students see pieces of this in several of my courses, and they need to memorize. It won't go into details in right now as I'm narrating, but in class we probably should go through just as reviews so everybody make sure they understand this. And this applies to all computers, with the exception of the memory mapped I/O here, is not necessarily on all systems. And there's always some kind of data and address bus and some version of all these elements. That's why I developed this minimal computer architecture. And then in this paper, I'm talking about microprocessors versus microcontrollers, and I teach all about microcontrollers as well as microprocessors. And this is a very basic difference here. There's lots of fine, detailed differences that we go into in other courses, not here. But the idea of having a microcontroller has all the memory and everything on one chip. All you need really is maybe a clock generator and a capacitor or something outside to connect the thing. It should be a single chip once your development's over. But the microprocessor is a different thing, different creature altogether. And it has a backside bus internally, and then everything off of the chip is a front side. Talking off a front side bus across the motherboard on PCs. There's different ways on different machines. So again, begin with a minimal computer architecture and then start sketching how things are different on different machines. And there's different clock speeds. The backside bus will be running the fastest because it's in the silicon and all the registers are right there. That's the fastest speed. Once you come down and go across the board in some kind of metallization, the printed circuit board, then you're going to run at a slower clock speed, and then the memory has its own clock speed too, or access time, whatever that's its clock speed. So you need to coordinate all that, as well as the I/O, which is listed as memory mapped I/O, or shown here like that. Although that's not always the case. And in IBM, we had separate processors on our boards. We had 20 processors on a board. 2 of them were just for I/O and would talk to an optical channel. And then we could put a whole bunch of boards, over 500 processors in one giant rack inside of a vending machine type of box. This is another slide from this intro class here. We're talking about PC design. All the students in the present iteration of the course have had this. Perhaps in the future I'll need to drill down in here to make sure people who have not had this or just have the homework assignment can make sure you know this. But this, we won't go into all the details here for PC design. Take a look at that in the lecture class, as well as the difference between North Bridge and South Bridge and how that's evolved over time, and the glue logic, which was over 50 chips originally on some of the beginning PCs, then got bundled. And this is into different North and South Bridge, and there's much more to talk about there. And then also the communications, where you plug in your boards and your graphics boards and other boards, and how that's evolved over time. And some of these slots are obsolete now. And then we not only have much higher speeds, but we now have multiple serial lines and packetized information within the PC, which, if you were alive 30 years ago, you would probably not believe that was going to be something people would do. That was, serial packetized communication was exclusive to computer networks 30-ish years ago. And then just showing the complexity of networking, packetizing, if you're going to do that kind of thing. And there's data, but a lot of overhead. This is a lab design project for the students in this course here, which is coming off of the books and being merged with one of the other courses. This lab, most of the students, all but one of the present students while I'm recording this, have had this lab, so I won't go into the details of it, certainly on this video here, but you can see that we have real-time versus simulation. And I've taught courses in simulation also. I always want to make a clear distinction between the two. A simulation that doesn't clearly represent the real time is just a cartoon that you can fudge to do just about anything. And we see that especially in robotics classes and other places too. So you can take time here and look at this at your leisure and pause this. And these manuals we develop in-house, and we've been doing that for 20-something years now, 23 years at Elizabethtown College. You can take a look at those. And then pause and do watch this video, even the present students, because this is just one group of the students of the past iteration of this course. But this is a good example of a bus, serial bus, connecting a number of different devices, PLCs and breadboards, and how they work that out. Now, the System 390s that I worked on in the mid 1990s were a bus architecture. As I mentioned already, there's a big vending machine, $1 million vending machine type of box, and in a very secure facility in New York, in many ways. And so we're going to drill down into the architecture of all this in later lectures in this particular course where I'm teaching this lecture right now. And the details here also we'll take a look at in class. Probably hand out copies of some of this that's hard to read in the PowerPoint. And more details of all that, how it all fits together, different pieces, with the course layout, and the evolution of that, how we switched from bipolar liquid cool, which was the fastest type of transistor technology, to CMOS. It took a little bit of a performance hit, but it eliminated the need for liquid cooling because the CMOS runs much cooler. And that was important for these $1 million machines anywhere, really. I mean, they run air traffic control in the New York Stock Exchange, as well as many military applications in the United States. But if you're selling these, which IBM very often did, to other countries where they don't have the capacity to keep the cooling going all the time, it's nice, mandatory if you're going to run your government, your banking system off of it. It doesn't have any downtime, and it's easily maintained. Here's another interconnect architecture, multi-stage interconnection network. Another one, a mega network. baseline network. Now the crossbar switch. So this is something that's I've seen more of, and a couple above there more obscure, novel kind of research things. The crossbar switch is implemented often as in, for example, the parallel sysplex that was being developed. Now, this was a group within my group that did just the communication. So the two processors I mentioned that were for I/O, for the I/O channel, the optical channel. We were optical back then in the mid 1990s. Within the facilities, with them connecting computers, as well as the IBM intranet, where we had leased lines, optical lines between the cities and under the ocean, so we could have a dedicated intranet that was secure. These machines, by the way, are very secure, hardware and software encrypted, and so as security issues become more and more of a concern, you'll see these kind of machines more and more valued when hacking and potential cyber attacks and ransomware proliferate as the future progresses. And then here's details I won't be reading through here, but in class we'll pause and read through some of the parallel sysplex details. Again, this wasn't something I worked directly on. I interfaced with this group. I understood how it all worked, but I didn't develop any of this because this was a whole separate thing from what I was developing. We had 1,400 instructions, including vector register instructions, in the machines that I developed, helped develop. And here you can take a look at the scalability of these dynamic interconnect architectures, primarily the bus and the crossbar switch. And I'll look at the IBM S390Z series that I worked on and still exist, have been quite profitable for IBM for many years, versus the parallel sysplex, where you can connect a bunch of these together, and other systems too, as well as you can hook a Cray up or Ascend workstations or Silicon Graphics or PC networks, or a number of other machines with the crossbar. And take a look at that. Pause and look at that.